welcome to session 1B, where we heard two fascinating talks by two of the fellows of our academy. The first presentation, I welcome Dr. Amit Agrawal from IIT Bombay, who will be talking on higher order transport equations. Why do we need them?
So, good morning, everyone. So, it's really a pleasure for me to be here, and thanks to the Academy for electing me as a fellow of with this prestigious Academy. It's a great honor for me. So, I will be talking about the higher order transport equations, something that we have been doing. And we will essentially at the end would like to sort of convince that there is a need to look beyond the conventional equations, which are, I'm sure everybody knows about them, which is like the Navier-Stokes equations, the most sort of celebrated equations, one of the most celebrated equations, something which appears in the top 25 equations of lot of Nobel laureates as something which has been revolutionized the way that we have been looking at physics and so many other problems. So, so here I'm trying to sort of say that the Navier-Stokes equations itself are not adequate, and we need to look beyond them. So I will present some evidence for that. And then the question arises, if Navier-Stokes are not sufficient, then what are the next set of equations? So I will introduce the so-called the Burnett and the Grad equations. And one can ask the question, is it possible to solve them analytically or otherwise? So we will sort of again give some evidence for that. And then we will sort of get into the ideas, why don't anybody talk about these equations? So we will say that, okay, there are issues with these equations, that's why it's not so well known with the community. So what are the alternatives and what are the more accurate equations? Is it possible to derive them? So that is the type of questions that we will ask. And finally, once we have these equations, how do we know that these are correct? So how do we benchmark them, or what are those benchmark cases and so on? So it's like quite a few points that I would like to sort of get over it. But the basic central question, thing that I'm trying to emphasize here is that it is these so-called the Navier-Stokes equations, celebrated equations that we have for the last 100 plus years are not the final word as far as the transport goes. And there are fundamental issues. It's not just that tweaking these terms somewhere or the other. So let me start off with what these Navier-Stokes equations are. So as we know that we have to conserve mass, momentum, and energy. These are the basic physical principles around which any equation that we derive are built on. So, the Navier-Stokes equation are essentially a conservation of momentum statement for conservation of momentum. So we start off with from the Newton's law of motion. So if you look at it, we have the mass times acceleration on the left-hand side. The forces are there on the right-hand side. At this stage, which is known as the Cauchy's equation of motion, the equation is not closed. That means that there are more number of unknowns. And we have to somehow, then the number of equations that we have. So we have to somehow generate additional equations. And so these stresses are the ones which appears as the unknown at this stage. And these stresses are then substituted into the equation using a constitutive relationship. So if you have Newtonian fluid, you will have one type of relationship. If you have non-Newtonian fluid, you will have a different relationship here. So this relationship, once you add that to the Cauchy's equation of motion, you have a closed system, and you can solve that. So that's essentially what is happening, and you can see that these mass, momentum, energy conservation equation as applied to a differential element, a small element of the fluid, is what ultimately is like being solved, whether we look at CFD, which is solving it numerically, or we are trying to do it analytically in whatever ways. So that's the sort of the background, and that's how things have been going on till now. And this works very well, so we can sort of define the domain in which this would work very well. So this is a continuum equation. So it works well when the continuum hypothesis is satisfied. And to be able to define what we mean by a continuum hypothesis, we sort of define this a non-dimensional number, so-called the Knudsen number, which is the ratio of the mean free path of the gas to the length scale. So essentially what we mean by continuum is that we sort of don't ignore the molecular nature of matter. Whatever fluid element we're talking about is large enough that there are too many of them, so there is average properties, etc., that you can take. So we don't have to worry about that molecules can, once they move or enter a control volume, they can bring in a lot of momentum or a lot of energy with that, and therefore there could be a lot of wild fluctuations and so on. So all those you can neglect, and that happens if the Knudsen number is very small, which means that the mean free path of the gas is much smaller as compared to the length scales over which we are looking at things. So, for example, if you look at air or nitrogen, under this condition, it is like 70 nanometers, whereas if you're looking at flow in this room, it is a few centimeters or meters, whatever is the length scale. So it's like nanometers versus centimeters, so it's very different, very far apart. So you can say that this is very, very small number and continuum assumption applies, and that's where everything in Navier-Stokes works very well. But now what happens is when the two length scales start becoming comparable, so you start moving on this Knudsen number scale towards the right, and specifically you go through these regimes, the so-called the slip regime and the transition regime, where, for example, in the transition regime, the two, we have Knudsen number of order 1. That means that both of them are of comparable magnitude. So this is where, we clearly see that the Navier-Stokes has difficulties in modeling these sort of flows. And these sort of flows do appear in a lot of different cases. For example, when the length scales are small, like whatever you see here in these sort of scenarios, when you're talking about small devices, or if you're looking at even the movement of air in our lungs as the time it goes to the smallest branches, the length scales can become very small and comparable. And Knudsen number effect can start becoming relevant in there. You can look at simple flows like tilling of soil and ask the question, how does the air reach the roots of the soil? And again, it goes through because of the porosity of the soil, and that's why we need to till the soil periodically so that these pores are maintained. So again, if you are looking at trying to sort of see, trying to model the air movement within the soil and all, you'll have to start bringing in the Knudsen number effect, which is sort of pretty much beyond what Navier-Stokes will give you. So similarly, if you're looking at high aircraft flight, if you're looking at gas centrifuge of interest to bar, for example, these are all examples where the flow starts coming into the slip and the transition regime, and it is beyond the purview of the Navier-Stokes. That's what we start to realize. And there are direct evidence of the Navier-Stokes failing. For example, if you take a very simple flow like a quid flow, where two plates are moving parallel to or in opposite direction but parallel in a plane parallel to the plates, you expect to get a linear velocity profile, which is what you get in the continuum regime. But once you start moving towards the slip and the transition regime, in the slip regime, you start to first get a velocity slip at the surface. But then, once you get into the transition regime, you see that there is a non-linearity which starts to appear in the velocity profile, which is something which the Navier-Stokes equation will not be able to model. It always continues to say that second derivative of velocity with respect to y is 0, which gives you a linear solution for velocity, which cannot be able to, because of which you will not be able to model something like this. Similarly, you can look at the Poiseuille flow, again, flow between two parallel plates driven by pressure, and you expect to get a parabolic velocity profile, and you expect to get a pressure distribution along the y direction, which is not changing. Whereas what a lot of cases, lot of data, etc., suggests is that there is a variation in the y direction, which means dp dy, you cannot say it is equal to 0, which is again something which comes from the Navier-Stokes. And then we have looked at other complex, so these are simple flow situations. We have looked at several flow scenarios, done detailed experiments for them. Like one example I'm showing here, which is a sudden expansion. We can have like a slowly changing cross-section. Here there is a sudden change in cross-sectional area. We can have a slowly varying cross-sectional area change. We can have bends and so on. So we have done detailed measurements in these cases, and we have found that one is not able, and there are a lot of sort of different or situations or the solutions that we come out or the behavior that comes out is very different from what we normally expect to get in the continuum. So that's one part, but the more important part is that we cannot model these flows again with the Navier-Stokes, and you not just are able to not capture these sort of local behavior correctly, but overall the gross behavior of the flow also turns out to be very, very wrong. So again, it's just trying to sort of expose the limitations of Navier-Stokes. We have also done measurements, for example, with heat transfer in tubes. And a very simple scenario again, something which was surprisingly not done in the literature. And what we find is that the Nusselt number or the heat transfer coefficient has a very strong precipitous drop with an increase in the Knudsen number when you go to the slip and the transition regimes. And something which again the Navier-Stokes equations are not able to give you. So I'm just trying to first expose the limitations of the Navier-Stokes and sort of say that this is a pretty generic sort of a thing. There are a lot of scenarios, lot of cases, not just isolated cases, lot of cases in general where one finds that Navier-Stokes will not work. So what is the alternative to model these flows? So with that, very quickly, I will bring out these two equations, the Burnett and the Grad equations. So we have seen that we start off with the control volume, and that's how we drive the Navier-Stokes equation. We showed you the Cauchy equation of motion that comes in first, and then you bring in the constitutive relationship and closure relationships. But so that approach, as you can say, it leads to Navier-Stokes, but it will not be able to expose the limitations of the Navier-Stokes. So you have to start off with an alternative manner, and that alternative turns out to be the Boltzmann equation, where if one starts from the Boltzmann equation and follows one of these two methods, these are well known for the last 60, 80 years, one can drive a whole hierarchy of equations. So for example, if I look at the Chapman and Scott method, one tries to drive the stresses that one would have, and depending on what order of stresses I'm getting in terms of Knudsen number, if I stop at Knudsen 0, I will get the Euler equation. If I get Knudsen 1, I will get the Navier-Stokes equation. And then these are well-known equations, and then we can extend this exercise and obtain the so-called the Burnett and the super Burnett equations. So you can see that the Burnett equation would have all the terms that are present in the Navier-Stokes equations and more, and therefore this becomes a superset of the Navier-Stokes equations. And similarly, one can go with the super Burnett equation, for example, which will be a superset of the Burnett equation and so on. So this is one approach that one can take, or one can, in the other approach, one can try to sort of, rather than trying to write a closure relationship for stresses, one writes an evolution equation for these quantities as well, which essentially becomes the second approach by Grad, and one obtains the so-called the 13 moment equations and the 26 moment equations this way. So this is just a very quick sort of thing of what is being done in this scenario. So we start off with the Boltzmann equation. Boltzmann equation has only one unknown, which is this distribution function f. So if you can solve for this f, then one can obtain macroscopic quantities of interest like density, velocity, energy, and so on. But finding f is not easy, and that's where the two methods that I showed in this slide comes into the picture. So this is how these are methods to give you or estimate an f, and once you have estimated an f, which I will not get into, so again you use some sort of a perturbation, and you say that, okay, what order am I truncating, and depending on what order of truncation you have for f, you can get stresses of different order or heat flux of different order, which upon substituting to into the Cauchy equation will give you these hierarchy of equations. So this is essentially what goes on in this method, and these are like, if you want to get, so if you were to do it at first stage, you will get you can show that you will get the Navier-Stokes or the Newton's stresses exactly, and whereas if you do it further, you will get the sort of Burnett and the heat flux. But let me point out that this is a purely mathematical procedure. So there is no physics anywhere that is being incorporated. You're just sort of doing a mathematics to get from F0 to F1 to F2 and so on, and you are trying to construct a procedure that way. And this is where the whole issue lies, that this fails because this does not capture the physics correctly. So there are a lot of limitations of these equations, and how many of us would have heard about these equations? I mean, probably very few have ever heard about the so-called Burnett equations, because there are a lot of issues with them. one of the most difficult, I mean, the biggest issues are that they fail to satisfy the laws of physics and they fail to satisfy the thermodynamics requirements. So they are not always entropy generating, for example. So it's a severe sort of issues with them. And that's why you see there are a lot of variants of these equations which exist in the literature. And similarly, one can look at the other approach, in the grad approach, where, as I said, that we try to write evolution equation for stresses. So we have the mass, momentum, energy equation as before, but then we have add the equation for stresses and equation for heat flux, and so it becomes a much larger set of equations with lot more number of boundary conditions that needs to be satisfied. And so that is where that's the alternative approach that we have. But again, even with all this complicated system of equations that we try to solve, we find that the solution does not improve considerably. So it is not really worthwhile is what people have found. And again, there are a lot of variants of these equations that exist. So that begs the question, is it possible to drive higher order or in an alternate way, and maybe where we try to bring in the right physics, and therefore whatever equations that we would get will be better. So this brings us to the third vertical, which is what our contribution has been, where we try to bring in the Onsager principle based sort of thing. So the idea here is that we try to write the distribution function in terms of forces and fluxes, which is the idea which goes back to Onsager. And this is a follow-up work from Mahindra's thesis, which was done in HBNI. We realized that that work, I mean, with certain modifications can be taken up here. So that's essentially what we did. And we sort of showed that once we start off with an approach like this, we can show that all the collision invariance properties and the other properties that you need in the equation can be exactly satisfied. And then you can subject these other distribution function, other equations, other distribution function that people were using to the same test. And you will find that the simple, very simple collision invariance property, which means that when the molecules are colliding, they should not be creating mass momentum of energy, should get satisfied, which the other distribution function does not satisfy. So with this approach, we are able to drive the alternate forms of stresses, heat fluxes, which are required to be closed in these mass momentum energy conservation equations. So these are the stress terms, the normal stresses, the shear stresses that we have derived now using our approach. Similarly, the heat flux is here. And so this is just a sort of, so these are a set of equations that we essentially get from our alternative approach. And if we start looking at what are the features of these equations now that we have, okay, so I will just take two more minutes and finish it off. So what we find is that our equations do not require additional boundary conditions. The stress terms do not depend on temperature gradient. These are some of the issues that were there in the earlier equations. And because we feel that we have started off with physically with a consistent approach, we get equations which are consistent. So none of these issues, including the issue of stability, including the issue of entropy not being positive, always, entropy generation not being always positive, all these are automatically satisfied without we imposing it at any further stage. In fact, once we choose a distribution function, there is a mathematical procedure that one has to follow, and there is nothing no arbitrary constants or anything that gets introduced with us at any stage. Similarly, one can drive the 13 moment equation approach to that, and we have been calling them as O13. O is for Onsager, just to sort of bring in the thermodynamic aspects. So the mass momentum energy equations remain as before, but if you look at the evolution equation for stresses and heat flux, now they're substantially different from whatever you were seeing earlier. And finally, one can compare at the same order what happens, because it's a different approach. We just try to show some consistency there. And okay, so I will just skip this part. And then finally, I will say that, okay, how do we know that these are correct? Now, these are very complex equations. As we know, Navier-Stokes is complex, and these are a superset of the Navier-Stokes. So how do we know that they are correct? So there are a very few benchmark problems that we have here. So here I would like to point out that this is one problem that we have introduced from our side. It was actually given in Grad's paper, but people have ignored it for last so many years, and we realized that this is actually a very good test case. And so we brought it, we called it as Grad's second problem, just like we have Stokes' first problem, second problem. So we called it as Grad's second problem, and we suggest that all the equations should be tested against this benchmark problem as well. So what I will do very quickly here is just to take one benchmark problem, show that the data that we get is consistent. So I will just go very, very quickly through this. Just to sort of show that we have compared our results, whatever we are getting from our equations, for one benchmark problem, but lot of different quantities, all the stresses as well as the velocity, temperature, density, etc. And we against lot of benchmark things, and we do get very consistent results. So I think this is where I will stop here. I will just sort of say that, okay, what we have tried to say here is that there is a definite need for looking beyond the Navier-Stokes, and the currently available Burnett and Grad equations have required additional boundary conditions. They are not thermodynamically consistent, and there are a lot of other issues with these equations, and that's why they are not, we don't really hear about them. So what we have done is actually proposed new set of Burnett and Grad like. We just like to use like here because they are not derived in the same manner. It's a very different philosophy from where we start and get these equations. And we sort of have proposed a new benchmark problem, and we also have shown that these equations are indeed accurate. So let me just acknowledge all the students who have worked with me over the past, theoretical work as well as experimental part, which I have not really talked about here. And finally, let me just dedicate this talk to my father, who was a professor in physics, who was, needless to say, was instrumental in shaping my life and career, and who we lost very recently. Thank you.
The experimental work that you referred to, does that pertain to experimental verification of the solutions of your new proposed equations? Or, I mean, consistency is one thing.
Correct.
But whether that is the physical reality is an entirely different story.
Correct.
So I just wanted to know what are qualitatively.
Sure.
What has been.
Yeah, so basically what we are trying to do is when we look at this problem and we look at, there are very few benchmark sort of a thing, and what you are saying is right, there is very little physical experiments that people have. Mostly people rely on DSMC or molecular dynamics and such sort of approach to give you the solution, which may or may not be, which is not physical experiment, let us say. So we have been trying to do physical experiments and generate, so we have a novel approach of looking at the problem. So we scale up everything and then we measure things that way. So we are able to then get far more information than whatever people have been able to get. So, and then once we have the experimental data, then that experimental data can be looked at. We have not done, I will be honest here, we have not really solved these higher order equations yet, but we have solved the Navier-Stokes, and as I was talking about in one case, we see that not just the local behavior, even the gross behavior, for example, for a given mass pressure drop, I should get the right mass flow rate through the system. Even that sort of a behavior, I don't get it right. And there is a gross sort of, it's not again 2%, 5% deviation, it's like 40, 50% deviation is what we start seeing. So yeah.
One more naive question, like you talked about collision invariance property. Like if you take Boltzmann equation or Jean's theorem, the distribution function is taken as a function of the conserved quantities. Is that covered by Onsager's symmetry principle?
Yeah, so here what we sort of say is that the distribution function that we do, whatever we employ, we explicitly check for it to say that, okay, so there are like a standard test which one can subject these distribution functions to. And so once we subject these distribution, so they should give you a certain answer. So that's essentially what I mean by this collision invariance that we are doing here. So that is there explicitly given as, in the paper, it shows that this test has been done and this is the result that we get, which shows that it has passed the test here.
Please join me in thanking Professor Amit Agrawal for a wonderful presentation.